My name is Matthew Emery. I'm the senior data scientist at a company called Embellis Inc. We actually have some pretty big news. We are on the cover of Bloomberg Business Week this week. So this was a very well-timed talk because I will be talking about a lot of work that I've been doing with them, but I've made an entirely separate package to show off what we've been doing. Yeah, and the name of this talk is called "It's Technically Possible to Write R in Production." It's going. Okay, great. So first off, just a quick disclaimer. This isn't an invitation to a language war. There are definite real use cases for R in production. That's why I did this talk, not just to make fun of R. Just an FYI, this guy with the sword, he's called a French immortal. He's the guy who decides what is and isn't French, and he gets a cool sword. I just thought that was a great idea for like a language war. Yeah, like in France, they get to decide what is and what is not French. And I do not think this is auto-incrementing. So, oops. It is not. Whatever. That means I get to control this. This is awesome. I'm in control now. So why R? R usually gets statistical packages first. Also, the canonical versions of a lot of different packages are written there. This is really important if you have some very complex models. A lot of the things that we deal with at Embellis are like quite complex and have only been written in R. And we can do that conversion into Python or into C or something like that, but that incurs a significant amount of development costs. And then I'm going to answer the question of what makes for smooth deployment. So if you're a data scientist, a lot of times you don't think about this until right at the end, but you should be thinking about it like right at the front. 4 aspects of this are reliability, testability, interoperability, and auditability, which basically means it always works, we know it works with everything that we've seen before, and I can prove that it worked 6 months ago. Okay, so an example. What we're doing with this is a Poisson regression. So I know that there are implementations of this in Python, but not in scikit-learn. So if you were to do like a naive implementation, you would have to write it from scratch. But it is very easy to write this in R. So what is a Poisson regression? Well, it's trying to predict a certain count of things within a certain period of time. Right over there, that's what a Poisson distribution looks like. That's what we're trying to predict. The example I'm going to be using is Prussian army horse kick deaths. This is the canonical Poisson distribution. It was made up by this guy. I will not even bother to pronounce his name. But yeah, he looked at all the Prussian army horse kick deaths and he said, oh, this is a Poisson distribution. And he became very famous because of that. All right, so let's take a look at the data. If you haven't seen R before, I'm going to do a quick rundown here. But we have the data, we have some deaths, we have the year, and we have the corps, which is like the part of the army that those soldiers are from. We also have another column called Fisher, but we do not care about Fisher. All right, so this is what a Poisson regression looks like in R. Also, the arrow is just like an assignment. So we load up the library that we need. We have the GLM, which is a generalized linear model. We say it's Poisson. And then we do a prediction. So this is count data, but somehow we predicted a negative value. That might be important. You might want to be able to check for that. So one of the things that you do when you put any kind of model in production is you have to define what your inputs and your outputs have to be. So one of the things that we will want to do is put a little bounding box and say anything negative should actually just be 0. All right, so if you have ever coded in R before, you're probably doing it wrong. I really recommend that you take whatever R code that you have in one-off scripts and just turn it into a package. There is a whole book on doing this called R Packages by Hadley Wickham. He's kind of like the god of writing R, but good. And the thing about having R packages is it actually opens up a ton of new options for you. You have all these like really great checks. A lot of times when people complain about R code, it's R code that is just like a one-off script, and it has not been checked at all. So there's all sorts of like weird naming issues. But yeah, this completely eliminates that. Hey, let's talk about reliability. So if I predict based off of, if I submit a request to any model, and instead of putting the I core, which is what we had for that data, I put in the first core, we're going to get an error. And not only that, if I submitted this as a data frame or some sort of JSON blob, it's actually going to fail out all of the things attached to that as well. That's no good. So what we're going to have to do is we're going to have to make sure that we strictly enforce like all sorts of checks on the input to the data. What does that look like in R? It looks like this. So this looks really weird if you haven't seen R before. But what you can see is that little percent check sign over there. You can call that like a then statement. So you take the data, then you verify that you have all the columns that you need. Then you assert that the year is within the year that Prussia existed. Then you select those columns, and then you filter to just those years. So this will give you a warning that, oh, hey, you have data that is out of bounds. We've removed it already. That's really important. Okay, so how do you do tests? In R, you use a package called teststat. In Python, you'll use something probably like PyTest. It is critically important that you unit test all of your data science code. A lot of people skip this, but it is so important when you put it into production. The reason why is when something goes wrong in data science, it often doesn't show up until much, much later. So you'll have something that you think works totally fine, but then all of a sudden, all of your predictions just don't work. And you'll go, oh, it must be because my model is off. No, it's probably somewhere before that. This is what a test in R looks like. You have an input, you have an output, and then all you have to do is you just assert that the function plus the input is equal to the output. So it's very similar to, say, like a unit test in Python or XUnit in Java. Okay, we're going to keep on going. Interoperability. The reason I originally wrote this talk is I experienced the worst bug of my life when I tried to call Python from R. Don't do that. Instead, what you should be doing, or what I recommend, is to set up a little microservice. Now, that's just a little server that is going to be doing just one thing. You're going to call that server, and it's going to give you a response, probably in JSON to JSON. And that means that it does not matter what language is calling it. You get back exactly what you want. You want to minimize the amount of R code that you're writing, generally, in my experience. Okay. So I spent 2 hours trying to get this GIF to work, and it turns out it does not work anymore. So this was just proof that I actually wrote all of this. You can actually go onto my GitHub. It's lstm Emery /horsekickr, right? You got to put an R in the end if it's a R package. But it is all there. We can completely predict Prussian army horse kick deaths at scale. Go ahead, deploy it wherever you want to. Okay, auditability. This is the last portion of this. So, say someone asks you 6 months from now, oh, how did that prediction happen? You should have an answer to that. This is really important, especially if you're in a regulated industry. It's not good enough to say, well, I'll run it again, and then find out that it doesn't quite work like it used to. This often happens because dependencies change over time. So what you can use is something called Docker. Docker containerizes everything, including like your C dependencies and the operating system itself. It's very easy to build a little Dockerized system, and you can have it stored away forever. So in my case, if someone asks me, hey, why did someone get what they got? I can pull out the exact model. All right, this is what a Docker file looks like. I could do a whole workshop on just writing these, but this is generally the kicker, what you'll get out of it. You say from blank, that's going to be your base image. You install some dependencies. You add the package that you're looking at. Install your extra dependencies from that package and install the package. Finally, expose a port, and then you run the little API. By the way, that little API kind of looks like a Flask API. And boop, that's everything. So I think I made it under time, right? Yep. Okay.
All right, questions? This is something of a trivial question, but I was curious what the bug you got when you called Python from R was.
Oh my God. So what had happened was within R, when it would boot up a shell, it wouldn't go to bash. It would only go to the original shell. And then trying to like change the library that Python, so when you have it in shell, it's going to default to Python 2.7, but it was all written in Python 3 code. So I would keep on trying to hit Python 3 code. Eventually I figured out how to do that, but then it caused like an awful dependency mismatch, which is why we Dockerize things now. But essentially what was happening was a silent dependency upgrade in the CSV reading package in R had turned all of my logical Yeah, I think it was all of my logical columns just turned to NAs without telling me. It was a very bad time. Yeah.
Plumber, single process, or what is inside Plumber and is it?
Yeah, so I believe it is single-threaded off the bat, but because it is just like a simple server, I think you can actually just have it run behind like Nginx or something like that, and then you can get it to be multi-threaded. Honestly, what I do is I just have it as localhost, right, and just call it from there, and this is just a way to like completely lock down all the R. So the majority of my team writes Python. In fact, like everything from this point forward will be Python, but we have a lot of people who like still write R in different teams. And we just want to make sure that that stuff is completely segregated away. Another way to deal with this would probably be like proto buffers would be another example to speed this up, for instance. And one of my coworkers actually tried R2Pi, which apparently works well, but I don't trust that. Any other questions?
Hello? Okay. So my question would be, I feel like sometimes it's hard to write test code for data science. So is it in terms of software development, you would test a functionality, but for prediction model, how would you like write a test for it?
Yeah, there's a bunch of different tests. The first thing that I would recommend is, like, first of all, you should be definitely testing all of your pre-processing code as if it is just regular code, and making sure that the prediction is separate from any pre-processing. But when you're actually trying to test the models themselves, you want to be testing for like outputs, right? So at least for me, I know what the absolute minimal score should be, and I know like how to get to that score. So I want to make sure that that is the minimal score of some set, right? I also know like certain kind of ranges that will be allowed, and also this isn't necessarily a unit test in the way that we think about unit tests normally. But we also check to see if the distribution of our predictions has changed over time. That's another really important thing to do. But that's not something that's necessarily a unit test, but it's more of like we're monitoring and we have like a running average or running median, really. Anything else?
Any other questions? All right. Let's thank Matt again. So we're going to do a quick changeover and get Bruce set up and have fun till then.
Yep. Joe.
All right, folks, we're ready for the next one. Just get Bruce to test his mic and give an introduction, please.
Can you hear me? That's a yes. Hi, I'm Bruce. I have a software company. We're using deep learning to make a better hearing aid. So I have an interest in audio and speech processing, and you'll see a little bit of that coming out in this talk. My slides are actually on a timer, but I have some tricky business to do here. So do that, then we're gonna do that. And then we're gonna do that. Not sure that completely worked. Let's see. No, it didn't work. Darn. Oh, well, that thing's going to pop up once in a while. Here we go. So just for context, here's what I'm not going to talk about, dogs versus cats. The reason I'm not going to talk about that is that's a classification model. It's discriminative. I'm going to talk about generative models instead. That's an example of supervised training. You have a whole bunch of labeled pictures of cats and dogs, and you train your model using those labels. We don't have that. So why should you listen to this talk? Well, you're here. But it's yet another way to create pretty pictures. It's a new way to do it. The thing that got my interest, though, was the thing on the right-hand side here, which is WaveNet, which is arguably the most successful generative model ever created. It's now in your Google phone, and it's related to this. So unsupervised learning. We train on just data with no labels. How can you do that? Well, the goal is to learn something about the structure of the data. So you can do things like clustering, and you can do dimensionality reduction, or you can try to learn the probability distribution of the underlying data. Generative models are a particular way of doing unsupervised learning. It's one where you want to actually learn the probability density of your data. So you can think of these x's as being the values of the pixels in your image, for example. So there's several ways to do this, GANs, et cetera, et cetera. The one I want to talk about is normalizing flows. It's the new thing. It's maybe a couple of years old. So why do we care about this explicit joint density? If we know it, we can just plug in numbers into it and generate a new image. That's cool. We can use it to classify things. We can use it to denoise. That's my interest. We can impute missing data. We know this. So normalizing flows are models that make that joint distribution tractable, because just tackling it head on is not going to work. But it explicitly learns it. And the way it's formulated, you train it by you maximize the likelihood of the data that you've got. The general idea of a flow is that you apply a series of function transformations. We'll get back to that. Why are they good? Once you got it, you can do exact latent variable inference, you can do exact log likelihood evaluation, and you've got very efficient inference and synthesis, and it actually has a useful latent space for downstream tasks like interpolation or modifying images and that kind of thing. All right, so what are they? You start with a distribution, which is something simple like a unit Gaussian, and then you apply a sequence of these bijective invertible functions f to your data until you get to the point where you've got a distribution that's complex and actually maps the data that you've got. And that's called a flow. So again, if your distribution in your data space looks like some complicated double banana thing, you want to get to a simple space where it's just some Gaussian thing. Now, when you do a change of variables like this, what happens to these probability densities? Well, there's this change of variable formula, and you get this sort of nasty-looking term that you see down here. That is the Jacobian. Well, it's the absolute value of the determinant of the Jacobian being all these partial derivatives of f with respect to the x's. And if you think back to your first year calculus, we did a change of variables and got extra terms like this in it. It's the same thing, just in more dimensions. Now, so have we really gained anything here? We traded one hard problem for another hard problem, because this Jacobian determinant, not trivial. So this is where the flow stuff starts getting clever. So real NVP introduced this concept of doing an affine coupling layer. So you take your data, x, you split it into two pieces, x1, x2. Half of it you just flow through unchanged. The other half you just apply an affine transformation. You multiply by s, and you add t. So the beauty of that is your Jacobian becomes a lower triangular matrix, and the determinant is easy to calculate. You just multiply everything that's on the diagonal. So everything becomes very simple, and it's still expressive because S and T can be anything, as complicated as you want. But wait a minute, we just passed through this stuff unchanged. How expressive can that be? Well, the good news is we can stack these layers one on top of the other. So in the next layer, we can just swap the role of x1 and x2, and now we're doing all the fancy stuff on the x2s, and there's other ways to make it even more complicated. Does it work? Well, the initial authors tried it. Mostly they were interested in image generation. They tried it on a lot of the standard data sets. Here's some celebrity pictures. We'll carry this through as an example. So they don't look great, but this was early days. It was kind of the first thing. But they do look like human faces, so that's not bad. The next step forward in this was something called Glow. They added a few things in their architecture which resulted in both better looking pictures that they were generating, but also this very cool ability to manipulate the latent space with semantic things like smiling, age, blonde hair, beard, and so on. So lots of examples here, but if you look at this one, the picture in the middle here is one of the real photos. It wasn't generated. But as you go to the right, it's sort of dialing up the smiling attribute on this. And if you go to the left, it's dialing down the smile attribute. So at every stage, you get a pretty good looking face, but with the characteristics changed the way you want. So these normalizing flows, very active area of research. Flow++ is something that came out of Berkeley just a couple of weeks ago, actually, and they want to address the issue that these flows are not quite as good looking as autoregressive models like WaveNet, PixelCNN, other things that do a really good job. They did some fixes there we don't have time to talk about, but the results are, okay, the pictures are now starting to look a lot better. They're getting a bit bigger. They also do a quantitative measure, bits per dimension, which is kind of, if you think of a compression, it's how well does it compress. And basically, they're kind of state-of-the-art in some sense for that measure. Okay, so I'm interested in speech. WaveGlow applies these notions, and here's the affine coupling layer here. Apply it to the problem of going from text to speech. And they got some pretty good results there. MOS is humans listening, and they're basically state-of-the-art there. So the summary is, the pros about these, they're easier to train compared to GANs mainly. Everything's relative. There's a useful latent space, there's exact inference, there's exact evaluation, and very efficient to do inference and synthesis, unlike autoregressive models, for example. The con is they're still not the very best for quality, but it's early days. That's it. And I must have been within my time because it was all time.
Sorry. Just hit the button at the bottom.
Okay, so I think this is on your third slide, but what actually is the loss function you're minimizing?
The what you do, maybe we can get well, it's basically this. You have an explicit expression for the probability density, and so you take the log likelihood of that, and that becomes the likelihood of your data. So you want to maximize the likelihood of your data.
What would be like a good hello world for normalizing flows? And are normalizing flows the same as flows? Like, are they always normalizing? Because I've heard some people talk about flows and without using the N word. So
yeah, no, it's not always normalizing. The terminology is still a little mysterious to me, exactly where the boundary between normalizing and not. So WaveNet, which I alluded to, is an example of an autoregressive flow. So it's not the sort of real MVP flow that I mostly talked about here. The hello world would be probably the real MVP stuff, and CFAR 10 or MNIST or something like that to generate digits that way.
And if I can follow up, are that sequence of functions, those are CDFs, right? The different flows? Or they're not?
No.
Okay. And is there a structure to it, like a BaseNet, or is it a linear sequence of things?
So the S and the T capture that sequence of functions, or in this case, it's a single operation. They can be, typically your neural net. In the case of WaveGlow, it's got some sort of WaveNet-like structures with dilated convolutions and so on. So you pick a network that's kind of congruent to your problem, but they can be anything that you want, essentially.
Yeah, so I don't fully understand everything, but if you want to contrast to a variational autoencoder, for instance, the latent space, and you're saying you have multiple latent space in this one.
Yeah.
And then the loss function in that one is just, I still don't understand why it works better than like a variational autoencoder or a GAN.
Sure, so, a variational encoder or a GAN, they actually, can I do this? This picture might help, or it might confuse things. Here's a taxonomy of these models. Basically, you can see that the variational autoencoders in this realm of the approximate density, so they're not, the whole point of the way you do a variational autoencoder is you approximate the densities to make it tractable. But in this case, we're making it tractable by choosing a particular architecture rather than somehow fudging the density. With GANs, you have just an implicit density, so it's quite hard to, you don't have your hands on it, especially. So if you take a real image and you want to go backwards through the GAN to figure out where it is in the latent space, hard. Not completely impossible. Some people are shaking their heads like, no, but you can sort of kind of do it, but in some iterative fashion. The use of the word latent space in the stuff I was showing, I don't like that, but it is the term that's used. This is not, usually latent space is reduced dimensionality, and that's how you get a more semantic description of your model. But in these cases, everything has the same dimension. Your data space and your Z space, where the Gaussian density lives, they have the same dimensionality. These are invertible functions going from one to the other. And that's why you can start in your data space with a real point and find the exact point in your, quote, latent space that corresponds to it.
Singan? Oh, great. So with the normalizing flow that allows you to actually like move a slider around, I'm guessing those have to be found, just empirically by moving things up and down.
No, it turns out that celebrity faces database, I just learned this, has a whole bunch of metadata associated with it. Like this is a person, and this person is smiling, and this person has light toned skin, and all these things. So they took all of those attributes. So say you want smiling attribute, and there's also not smiling. They took all the smiling ones, they took all those images, transformed those back to the latent space, averaged that vector out, also averaged out the vector of all the not smiling things, took the difference between them, and that became the direction in which they traveled to make more smiling or less smiling.
Any further questions?
Cool.
Have you actually done this for your company, Bruce?
I played around with WaveGlow a bit, and the jury is still out on whether that was a useful thing to do or not. Yeah, very early days for these things, but promising.
Cool. All right, let's thank Bruce again.
Is there a volume slider on it or something?
I thought there was.
No. Hello, hello. Is it working? Is this thing on? Hello.
Ask if they can hear you at the back.
Can you hear me at the back? No? Yes? Yes? Is that a yes or a no? Yeah? Okay. 1, 2, 3. Okay. I'll just try to speak a little directly into the mic. Okay. So I'm going to be talking about these series of models called knowledge tracing machines. But to start, who am I? I'm Jordan. I'm a web developer, or previously a web developer, as you can see by the picture on the right there. But this summer I'm going to be going back to school, going to UBC to pursue a bachelor's in computer science. And so today I'm going to be talking about these series of models called knowledge tracing machines. And these are models that allow us to learn the difficulty of questions and skills and allow us to predict performance of students answering those questions. So what we can do with this, what we can do by learning the difficulty and predicting whether students can answer questions correctly or incorrectly, is create adaptive teaching policies and begin to kind of, down to an individual basis, optimize learning. But first, we need data. And we're going to need a number of data points to do this. So the data points that we can capture are going to be students, the questions that they attempt, the skills related to those questions, and then we can count the attempts or count the number of times those attempts were correct or incorrect. And since this is a lot of data, we need a way of encoding this data, and the way we do that is with sparse encoding. So sparse encoding is just a way of structuring our data set. And we tell in this case, we want the computer that may assign meaning to larger numbers, say student 28 versus student 76. We don't want them to assign meaning to that difference in the size of the numbers, so instead we encode these students or questions as just zeros and ones. So for example, the student attempting the question we encode with a 1, everybody else is a 0. The question being attempted is a 1, and every other question is a 0. And here, users as students and items as questions. So now we've talked about the data. We can talk about the work that comes before the knowledge tracing machine. So first up is the item response theory model. These models encoded students and questions. The output being whether the question was answered correctly. While these models were good at predicting question difficulty, they tended to not learn how students improved over time very well. So the next models that came after that were additive factor models and performance factor analysis models, or AFM and PFA. These series of models encoded the attempts at acquiring a skill, and that was done by answering a question, but they didn't encode the question itself, just the skill related to the question. So AFMs count the attempts at learning a skill, and PFAs encode the number of wins and fails at acquiring a skill. So our metric is the area under the curve metric, and the curve that we're talking about here is the receiver operator characteristic curve. Without getting into too much detail, this allows us to select for models that achieve significantly better false positive and true positive rates than random chance. So how do the models compare? Well, turns out on this particular data set, IRT gets a better score than AFM and PFA. This is a little bit confusing because the other models came later, but we can kind of think about why this is by just thinking about the data set. Particularly, these models are very sensitive to the data set. So while IRT performs better on this particular data set, it's not always guaranteed to always perform better. It's just a quirk of this data set. Perhaps it could be due to the number of attempts per student per question on this data set are relatively low. So now we can talk about knowledge tracing machines, or KTMs. These models encode students, skills, wins, and fails. Recall that IRT was just students and questions, AFMs were skills and the counting of attempts, and PFA was skills and counting of wins and fails. So I mentioned that we count the wins and fails at acquiring these skills. And to help explain this, I'll use this example. So here we have user 2 attempting question 2, which is made up of skills 1 and 2. Their outcome was they answered it correctly. So the next time they attempt anything with skills 1 and 2, in this wins vector here, we have a count of +1 added to the wins. So the true power of KTMs comes with the factorization machines and the learned embeddings. So a factorization machine is a way of embedding extra multidimensional information about your existing data. In this case, we learn extra information about students, questions, and skills. From now on, we'll refer to this as side information. We can see this here represented by that vector V at the top. So that is just a multidimensional embedding about the students, questions, and skills, or users are students here, and items are questions. To give a little bit of intuition about how this, what this side information is, you can think of it as follows. The side information for questions and skills, you can think about it as those questions or skills difficulty, and the side information about students is that students' ability to learn these questions and skills. And we can actually plot this intuition if we set the dimensionality of the side information to 2. So on this graph, we can see that this student, Wally, is correlated with all these items and skills, and they're actually correlated by the dot product. So since skills 2 and 7 have a negative dot product from student Wally, they're negatively correlated, and this actually reflected in the data. We can look and see that they don't do well on questions that contain this. So here's how all these models compare. Note that MIRT there is just IRT with side information as well, and those numbers represent the dimensionality of side information. So you can clearly see here that KTMs on multiple data sets perform significantly better, or at least a little bit better, especially when we incorporate side information. So the computational cost of these is that even on a CPU, you get significantly faster training times and better performance than like its deep neural net counterpart, ranging from 4.5 to 32 minutes, and that just depends on the dimensionality from 0 up to 20, the dimensionality of the learned embeddings. And finally, I want to talk about some acknowledgments. So this work was all done by Jill Gen V, who was very helpful help preparing for this presentation, answering questions over email. And you can find working examples of all this stuff at his GitHub, some slides that were presented at AAAI, and the research paper at Archive. So yeah, feel free to check those out, and thanks for listening.
Is this technique built upon factor analysis, like basic factor analysis, which I think uses PCA and like rotation or something like that? Is it coming from that same line of? Do you know?
I'm not really sure. Sorry, I don't know.
Okay, cool.
Okay, so the goal was to predict, given a set of questions that a student had answered correctly or incorrectly, the goal was to predict whether they will answer a subsequent question correctly. Mm-hmm. Do you think you could modify it? So, and you also have to encode what skills a particular question uses to answer. Do you think you could imagine modifying the system so that it would work where you don't actually explicitly have to tell the algorithm what skills a particular question requires?
You could, and that's sort of what the IRT model does, that it just uses the questions. But I think what was found with those subsequent models and this model is that the skills can translate across different questions. And so they found it particularly useful when trying to predict, like, when you're just encoding the questions, it wasn't apparent which skills were present. I guess your model could learn those skills implicitly, but I think they found that explicitly telling it which skills got better performance, but I'm not 100% sure on that.
Okay, I can ask another question. The AOC actually felt a little bit low to me. Does it seem low to you?
It seems a little bit low, but like considering that it was, it performed significantly better was, I thought that was pretty cool. I'll actually just click on these slides here. There's an implementation of the deep neural net counterpart plus an extra little bit of like learning about individual students that gets a much better score. But let me just find it here. So you can see here that this is like the deep neural net counterpart without this extra little piece added on. And then when we go here, so this DKT DSC learns like about individual students' ability to learn, and you can see that it achieves quite a good score. So the idea here is that like these models learn generally how hard certain skills would be, but then once you incorporate extra information about how students can improve, then you can boost that AUC score quite a bit.
Okay, I can ask one more question?
No, but I can tell you the answers. There's some other stuff there.
So these factorization machines are very common in recommender systems. Mm-hmm. So I think they are trying to apply techniques from recommender systems into this question prediction. So I have a question. How does this work with missing data? Like if you have like some of those questions missing or incomplete data, that's what I mean. So
I'm not sure. I didn't see any examples or read about any examples that had missing data, but that's an interesting question. I haven't really thought about it.
Okay, so maybe because the AUC is a little bit low, maybe we could flip the analysis around. And do you think you could use it to identify questions that are badly posed? So questions where there is a lot of randomness in whether people are getting it right or not.
Yeah, I mean, going back to that, this sort of plotting, like when you can plot things like this, you can definitely see like look for clusters of users, clusters of questions. Like if everybody is getting questions wrong, like if you see here, question 5 is super far away, super negatively correlated. Like maybe it could be the case that everybody's pretty negatively correlated with that question. So using these, like using the factorization machine to learn these implicit things about the questions and skills and students, I think you could do that for sure.
Maybe just following on almost from that point, you could think of this in terms of almost like emulation, where you're trying to understand a student's ability, and you have knowledge of this latent space, you have knowledge of the question latent space. You could use that to build up an understanding of, okay, well, what's the question that I need to ask next in order to sort of, with the highest uncertainty. Maybe you could sort of think about it in those terms. So choose a question with the highest uncertainty. This is going to tell you a lot more about the student's ability. That's something which we could already predict quite well.
Mm-hmm. Yeah, I think one of the interesting things about this was, I think in the original paper they brought up like combining this with like a spaced repetition system of learning. So like seeing which questions over time were they least likely to get correct. So combining it with, all right, we're gonna give people questions at the time when they're most likely to like forget them, so that we can optimize their learning and make sure that we're not like just giving them all the questions they know the answers to already, but giving them the right questions at the right times.
Thank you for your presentation, too. There's a small question. How can you calculate the deep neural net in an hour?
Pardon?
You have a figure about deep neural net in an hour. How could you get them out?
So that was in the original paper. They used this, the metric was the DKT model here. And that DKT model, when they trained it on a CPU, took an hour to train.
Move on.
So are the factors the skills? Or are they the axes on that graph, maybe?
The factor and factorization machine?
Yeah.
I'm not really sure. I think the factorization machine is just the term for learning the embeddings. I haven't done too much reading on the factorization machines themselves, so I'm not 100% sure of like the origins of the term and stuff like that.
I can answer that question. Actually, so this is like the work I do at my job. So the factors that we're talking about here are like, so skills is one factor, but you also have the skills of like student would be another factor. And then you have another one that's, what was that, wins, losses, or attempts?
I think they did it for students' questions and skills.
Yeah, so it'll be like a quadruplet tuple that you'll be trying to factorize instead of just like a single matrix.
Any more questions? Cool. All right. Thanks, Jordan.
Thank you.
Let's thank him again. Can I just get a show of hands who hasn't put their name into the iPad yet? Just one. That's amazing. Well done, guys. Thank you, Lexi. Missed you. Just get you to test your mic and introduce yourself, Matt.
Yeah, so my name is Matt, another Matt here. So I work with Bruce here doing deep learning and audio, trying to build a better hearing aid. That's the fun project we get to play around with. And today I'm going to be talking about representations of audio for deep learning. So to start it off, I'm actually going to start with some images, but this is going to make sense in a couple minutes. So we can see that from 2012 to 2015, we made great strides in image recognition. This is a famous competition to the point we're actually beating a human's ability to interpret what's in an image using deep neural networks. This was, okay. And so these are a few other pretty cool results we have. So creating a caption from an image, segmenting every pixel out, or even here where we've got big portions of the image missing, we're actually able to fill all the pixels back in. And just a couple more on the top. We take the image on the face on the top, try to make it look as if it was the person on the left. And the images in the middle are kind of the combination of the two. And down here, they're actually using Wi-Fi signals to estimate pose through walls. And now for audio, we've seen a lot of similar results here, where at 2017, Google's speech recognition actually surpassed the human's ability to recognize and interpret what's in speech. And there's been a lot of other stuff. So the most common ones that we deal with are either the speech to text or text to speech. We also have the cocktail party problem, which is separating multiple speakers from a single microphone. That's been more or less solved in the last few years, and it was a long-standing problem. But why did I bring up the images? Every one of those results, and most image recognition research, is based on this two-dimensional convolution. So it's got a few different flavors of it, and there's different ways of combining them, but it all really comes down to that single architecture. This is probably my favorite paper I've ever read, and I'm not really going to do it justice, but take a look later. One way to interpret it is that the high entropy of a convolutional neural network is actually a clean image, showing that the CNN actually does represent image as well. So on the audio side, this is Talkotron. It's part of a text-to-speech system. It uses a mouse spectrogram, lots of LSTM layers, and they just kind of casually point out that WaveNet mixed with logistics, which Bruce taught us about. And now WaveNet. I'm ignoring the whole back end of it, but how you actually do inference with WaveNet, once you've got that distribution figured out, is using a one-dimensional dilated convolution to sample out of it. And then for speech recognition here, up until recently, this Caldi, which isn't even really deep learning at all, it has some MFCCs, which I'll mention later, hidden Markov and Gaussian mixture models. So this is another way that we're representing audio to try to get information out of it. These are a few more recent and fully deep learning speech recognition. They both use MFCCs, which is basically JPEG compression on audio. But one uses a neural network, the other uses an LSTM. Now we've got speaker separation here, a little closer to what we're working on. And they actually create a big embedding space that they try to cluster based on this spectrogram here. So everything's back and forth with the Fourier transform in this model. These guys call this time domain. It's called TASNet. But basically what they're doing is learning their own representation like a spectrogram and doing a non-negative mixture of those. And then you can the separators, there's different versions of them. WaveUNet here, a new idea. We're doing a UNet on one-dimensional time domain audio. So the last three were all solutions to the same problem, but all using very different representations of the audio. So spectrograms are really nice. They're pretty natural to use and often used, but they have a big problem with the phase. We can talk about later, and especially in the noisy situation, the phase looks almost completely random. The dark spots were just cropped out. So this one paper here actually interpolates between discrete representations of phase to try to reconstruct the phase. It's quite a bear of a model and not a very elegant solution to the phase. And then the next one here is doing a UNet, just like we do on images, on a spectrogram, but actually using fully complex convolution. So you maintain complex arithmetic the whole way through the UNet. Then invert back to audio with the complex numbers. And yet another way of trying to deal with phase is just directly predicting both the real and imaginary components. But this is a little awkward because of how highly correlated the real and imaginary are. And you can't be doing different predictions of them. So kind of in summary, for deep learning on images, everything kind of comes down to this two-dimensional convolution neural network and modifying that base for whatever you need to do. Oh, you're one more slide left. Of course. And then, so on the audio side, we really don't have a single representation of audio like we do for images. So it's possible, it's just a harder problem. It's possible we're waiting for the AlexNet or the CNN, go back one slide. It's possible we're just waiting for the CNN that we haven't found yet. And yeah, so this is a problem that I'm kind of actively trying to solve. And that's it.
So with images, we have like networks that are pre-trained on ImageNet and then fine-tuned. And with text this last year, it was like, oh, all these models where you learn all this unsupervised stuff and then fine-tune. Is there an approach like that with audio? Can we learn this audio space and then fine-tune?
At this point, no. There's no general architecture
and why not?
like that.
Is there something fundamental there?
I don't know. That's kind of the ultimate question. You have a little bit more to pay attention to with longer range dependencies. Basically, everything I talked about was speech related. So that actually narrows it down, and we still can't really come up with something. There's a little bit of transfer learning, like helping speaker separation based on an embedding space you get from speaker identification, but it's nothing like we have in ImageNet.
You shouldn't be surprised that you can't transfer learn in this domain. You should be surprised that you can transfer
I have a question about Wave UNet. It went too fast. I didn't get how did they get to two signals?
So it's basically like using a UNet for image segmentation, but just in a single dimension. So your input is generally like a single audio channel, and you do the UNet, and your output is two audio channels, just like you would predict multiple image channels.
Okay, so basically the result of this upsampling is kind of like something that reflects the structure of those two signals, kind of thing. That's how would you interpret that?
So this paper is actually doing music separation, but I'll call it speaker separation because it'll work for that. Basically, your mixer audio is the two speakers speaking over top of each other. And then one of your outputs is one speaker isolated on their own, and the other output is the second speaker isolated.
Okay, thanks.
What's the phase problem? I missed that.
Basically, to do deep learning in audio, we don't have one general architecture that works well for a lot of different problems. We've got 100 different architectures that work well for often the same problem exactly.
The question is about phase.
Phase. Sorry, I missed that. So this image is a bit hard to tell, but you can see the color scale goes from this blue to red, and we're actually wrapping over quite quickly in the phase. Sorry, so a spectrogram, in this representation that we're most used to seeing, we're actually showing just the magnitude of the spectrogram, because it's actually a complex number. So you have real and imaginary components in that number. So we normally just plot the magnitude of those two components together. But the phase then is actually the angle of that, if you imagine it as a vector in Cartesian coordinates. Phase is the rotation of that vector. So it comes from the fact that a spectrogram is a complex, or the Fourier transform returns complex values. So the phase is a difficult to represent portion of that.
I wanted to ask about the wave unit and splitting music that you talked about in the paper, that it did in the paper. Say there was like 3 channels, like drums, guitar, and vocals. How would it know which ones to separate out, or would you have to specify more channels depending on what you think is going to be in there?
You have to tell it beforehand what, like how many channels of output you want. So you might have like a vocals, a drums, a guitar, and then an everything else. Or you just ignore the everything else and just have the 3 outputs. So they need to kind of be predefined.
So if I understand, or this is kind of like a more general question, when we're doing all this image stuff, you've got some really cool applications like medical and things that it's useful to see. When you've got audio stuff, you're kind of divorcing it from like I'm thinking of that graph you had with like human ability to discern audio. Is we use like lip reading a lot, right? And so, like in terms of applications for this audio stuff, could some of it be useful if we also had vision in it?
Yeah, there is kind of almost a branch of the speaker separation that uses video as well. And so it helps separation, and they also predict, like show who's speaking. So that's definitely something that's being looked into.
We see a lot. You showed a lot of models today, which is super interesting. I was wondering, what I couldn't catch is do any of them use both the time domain waveform as well as the spectrum in one model? Or is it either or?
The only thing that comes to mind is...
And if not, why wouldn't you expect maybe some gain if you did that?
It's a good question. So the only one I can think of that kind of marries the two is this Tacotron WaveNet, but it's hardly even a single model. They use MEL spectrograms, which is almost a standard spectrogram, but then the WaveNet itself is generating single samples at a time. So they're not doing it in parallel, I think, is like you're kind of saying. In theory, we shouldn't need to, because we should be able to encompass all the information as a single representation.
Different representations have different things that are easy to extract from them, maybe, right? So you might get some things from that and some things from the other.
Yeah. Yeah, so maybe that's worth looking into. I haven't seen it done explicitly yet.
So I was wondering why you can't just input the phase and amplitude or magnitude in 2 separate channels, rather than using the real and imaginary components.
Yeah, I've tried it, and Short answer is it just doesn't work too well. Typically, you're working with, if you're using the spectrogram, you're probably doing stuff similar to image analysis, basically, on it. I'll go back with the phase. My theory is the fact that the phases are wrapping over so quickly presents an extra challenge where you have no smooth gradients. It's not like it wraps over the course of 12 bins or anything.
But there's still some structure. But there's still some structure in that clean speech phase.
Yeah, there is some. All my tests have been unsuccessful with that. So the easier way to do it is you actually create a mask based on the magnitude, and then you apply that mask to the phase as well, and you invert with the noisy phase. So that's a decent first attempt.
Hey, I'm going to use my host abilities. So you showed the deep image prior. Yeah. Has anyone done deep sound priors as a way of measuring, say, how good architecturally all these different models are?
Bruce tried deep image prior on a spectrogram and didn't get anything useful out of it. But I haven't seen any deep sound prior on anything else done.
I'm going to use my host abilities to ask a question. You made a point of pointing out complex numbers are being used in the various networks here. Is there much of a gain? Like, are we gaining very much other than like just knowing how to do math slightly better around multiplication?
On certain evaluation metrics, it's a drastic difference. Because say you're doing a mean squared error between waveforms, if you invert the phase of everything, your mean squared error is terrible, but the audio sounds the same. It does get, the actual quality of the audio does increase, albeit usually by a small amount. It doesn't really change results too significantly. It's just an extra, incorporating phase is just an extra little bonus.
Thank you, man. There's more question. Maybe you or anybody can help me for the big data, and everybody will know that. But now there is some forum. They said about deep data. Have you heard about this one?
Sorry, which data?
Deep data.
No, I'm not.
Okay.
Not familiar with that.
Yeah. Okay, thank you. Because I asked Google, Amazon, or Microsoft, nobody knows that.
Okay.
Thank you.
Yeah.
We have time for one more question if there's one out there. Oh, we got a taker.
I was just thinking about that Google graph that you showed, that they're better than humans.
Yeah.
Any chance you know how they actually measured that?
I don't.
Didn't think so.
Yeah. Yeah. Probably with Google's version of Amazon Mechanical Turk.
All right, let's thank Matt again.